This is lesson 48 of the Quantum Mechanics, a mini lecture series, Schrodinger's equation part 3. So what I did was in the previous video, I came up with these, previous video, these two expressions. Okay. Partial derivatives with respect to x and time. Here's what I got. Right there. So what this means is the p squared over 2m psi is equal to this here, and the e psi is equal to this thing here. And so therefore we can write the following expression: dx plus v of x. So this is the potential energy term. That's the kinetic energy term. So Ke kinetic energy, Pe potential energy is equal to this. This is the famous time-dependent, time-dependent Schrodinger wave equation. Time-dependent because it depends on time. Okay, the wave function depends on time t. Wave equation. And the solution to the Schrodinger equation describes how the wave function changes as a function of space and time. So from before I had this, right? That's the solution to the equation. But a limitation of this is that it doesn't tell us how the particle moves through space, okay? Newton's equations tell us how the position and velocity of a particle vary in space. Schrodinger's equation tells us how the information about the particle changes with time, just the information. Okay, and this equation is very important. It's very significant. In fact, all of chemistry is described by this equation. Okay, you could describe in principle all of chemistry, how molecules behave, how atoms bond together. It's a very important equation. To get the time-dependent case, I should say time-independent case, we'll assume the wave function looks like this. Okay, that should be a small psi. E to the minus I e t of h bar. Okay, to get the time-independent case, if we plug this into the time-dependent case up here, we'll get the following expression. Okay, very, very messy, but it's just plugging it into what we have from before. E small psi x e to the minus I t of h bar. Okay, you can check this for yourself. I'm not going to do it here. Now, we can actually do some cancellation here. We can actually cancel out this term from both sides of the equation, right? And after doing some rearranging, we can arrive at an expression like this. This is the time-independent Schrodinger equation. Okay, so there's two different forms of the Schrodinger equation.